not sure this really helps, but. Helping?
No.
Yeah. All right.
Making the streets blurrier.
Okay, well, I'm sure that's better or worse, but, okay. So for a general square invertible matrix A, solving X equals B, we have an algorithm now, LU decomposition. So you perform Gaussian elimination that gives you LU, you know, with some kind of pivoting. And then you apply forward and back substitution. But today we're going to look at a couple categories of matrices. And see what the process of solving X equals B is like for them, and how we can proceed most efficiently to take advantage of what we know about matrices in these categories. Okay. So the first type of matrix look at are banded matrices, which go about quite often in nature, or in applications. Okay, so first I'm going to define some terms. N by N A as the following. Okay. Upper bandwidth. Okay. P, if the following is true, if Aij equals 0, where J minus I is greater than P. All right. The most extreme case of upper bandwidth is if you have, for instance, a lower triangular matrix that has nothing in the upper triangle, then that would be upper bandwidth of 0. Okay. The message about me potentially being a hiring manager was just recalled and then sent again. He was sent where everything is always in order. Okay. Okay. So we have lower bandwidth. Q. So it's the opposite case, Aij equals 0 for I minus J being strictly greater than Q. Okay. And then so then is banded. We say that A is banded if the total bandwidth simply banded, which is P plus Q plus 1. P for upper bandwidth, Q for lower bandwidth, and 1 is for the plus 1 is for the main diagonal. It is less than 2n minus 1 for an n by n matrix, because a matrix that is completely full, all entries non-zero, has a maximum possible bandwidth of 2n minus 1. So anything under that is banded. Now, a matrix that's mostly full, like the n by n matrix that has bandwidth of say 2n minus 3, that's not interesting. We're interested in cases where the bandwidth is very small, like upper and lower bandwidth of 1, for instance. So, I'm going to draw an example of a banded matrix. This 5 by 5 matrix. So here's the main diagonal. And then we have the lower band here. So we only have non-zero entries in the first diagonal that's below the main one. So the lower bandwidth Q is equal to 1 in this example. And then above the diagonal, here's our upper band. So we have non-zero entries in the first 2 diagonals above the main one. So the upper bandwidth is equal to 2. So the bandwidth of this matrix is 4, because we throw in the main diagonal. So there are 4 diagonals that hold all of the non-zero entries in this matrix. Some subcategories of banded matrices that are of interest. This one especially, tridiagonal. Is if P and Q are both equal to 1. So we only have entries immediately above or immediately below the diagonal we're on it. Another one that comes up not nearly as often, but I've seen it now and in various papers. Pentadiagonal. So P and Q are both 2. So the names come about because this one has a total bandwidth of 3 and 5. Now, we see banded matrices most often in applications involving differential equations. If you're approximating derivatives by finite difference formulas, then those lead to systems involving banded matrices, so especially tridiagonal ones. Okay. So in fact, this next example I'm going to give is from that. Any questions so far? So you approximate a second derivative of a function. By this finite difference formula. That we've not dealt with in some other class. Then there's some error that's on the order of h squared. So this leads to this tridiagonal matrix that has, so we're evaluating the derivative at x, and here we use the function value at x. So this leads to minus 2's the main diagonal, and then 1's above because the coefficient of this term is 1. And the coefficient of this term is also 1, so these 2 1's below the diagonal. I'll get to that in a second. So So if I let U be equal to values of the vector U consists of values of a given function U on n equally spaced grid points, x1, x2 up to xn, then call this U2, which is meant to be the second derivative at the same points. Can be approximated by 1 over h squared times a times u. So multiplying your vector of u values by this matrix carries out this finite difference formula, applies it to the u values to produce approximate u double prime values. On the assumption that at points immediately to the left and right, if you give them as boundary points, are both 0. So because at your first point, you're using your second point and a point to the left of it, but you don't have that. So if you just assume that that value there is 0, then you have a still unreasonable second derivative value. Otherwise, you would need to add terms onto this to account for boundary values. For instance, boundary conditions that come from a boundary value problem. I want to focus on just this matrix A, which is actually why I left out the 1 over h squared. Just a 5 by 5 example of it. Show you what happens when we carry out, when we compute its LU decomposition.
Need you to hire somebody.
Hire somebody to do that for you, so you don't have to do that again.
So the 5 by 5 instance of it, so I'll fill in all the entries. 1, 1, 1. Wow, this matrix is really crooked. 1, 1, 1, 1. Wow. Okay. Okay. And A equals LU. And we know something about what L and U look like. You know, L is unit lower triangular. But something interesting happens with the entries below the diagonal multipliers. Fill in the general structure of U also. Okay, so for L, we have a nice pattern here. We have -1/2, -1/3, -1/4, -1/5. But what's more interesting for today's topic is the fact that everything below that is 0. And then if we look at U, we have, okay, so on the diagonal, we have -2, and then -3/2, -4/3, -5/4, -6/5. And then above that, we have 1, the same ones that were there on the super diagonal originally. Like that's everything. Diagonals below the main are called subdiagonals. Diagonals above the main diagonal are called super diagonals. Right. So what we see is that, okay, A has upper and lower bandwidth of 1, being tridiagonal. And we see that L has also lower bandwidth of 1. And U has upper bandwidth of 1. So in general, when you compute the LE decomposition, whatever upper bandwidth and lower bandwidth that A has goes into the same for U and L. So in general, if A equals LU, then L has the same lower bandwidth of A, and U has the upper bandwidth of A. Okay. So then, what about the efficiency of Gauss elimination or LE decomposition for such a matrix? So for each column of A, you only have to eliminate P entries. That's how many you will have below a diagonal in each column. So we have order n times P row operations to perform, as opposed to order n squared for a general n by n matrix. But then what about the work involved in each one? Well, what you're doing when you perform a row operation, when you're working on that row, you're updating entries that are to be to the right of that column in that row. Okay. But also what happens is if you're taking a multiple of row J and subtracting it from row I, if the entry in row J is 0, then there's nothing to update. No change is going to happen. So when you're taking row J, you're going to subtract a multiple from it, from each row below it. But the number of non-zero entries in row J past the diagonal is at most Q. So in each row operation, you're going to touch at most Q entries in each row, but you update. So the order of Q flops or floating point operations per row operation. So the total amount of work is order n times P times Q. For Gaussian elimination or LE decomposition. In other words, having a banded matrix knocks 2 orders of magnitude off the amount of work needed for Gaussian elimination. Gaussian elimination in general takes order n cubed flops, but say for a tridiagonal matrix where P and Q are both 1, it's going to take only order n. So the amount of work is minuscule compared to the general case. Question so far. All right. Okay. Well, there were half a class on banded, half a class on the other category, symmetric possible definite. So far so good. Okay, so now I want to show you how do we carry out gas elimination efficiently for a abandoned case. Because, and you've seen the algorithm for a general case. Of course, it could just run that. We want to modify the algorithm to explicitly take abandonedness into account. What I'm going to do is write out the original gas elimination algorithm that you've seen before. It only apply to A. We don't care about B right now. And then see what we can simplify. Well, from a tri-diagonal case, I'll limit myself to that. All right, so the original algorithm. All right, so for each column, we go to each row. And then within each row, we compute the multiplier. And then we carry out the row operation. So keep in mind that in each column, we only have to perform one row operation. And that row operation will not have many elements of that row changed to the upper bandwidth. Let's see what we can strip out. So first of all, in column J, the only entry we actually have to eliminate is the entry right below it because of lower bandwidth 1. So I is just going to be J plus 1. So this loop no longer needed. And wherever I see I, I'll just replace it with J plus 1. I have Right, so that's one optimization. Oh, well, I need to do the same thing in this inner loop. Okay. So let's take a look at this right here. K starts at J plus 1. Now, because of the upper bandwidth of the matrix, if a column index is 1 greater than the row index, that means we're on the super diagonal. So we will have a non-zero entry there. But so this first iteration, K equals J plus 1, that will be needed. But once the K goes to the next value, J plus 2, well, J plus 2 is 0 because for a tridiagonal matrix, if a row and column indices differ by more than 1, the entry is 0. So that means that K is only equal to J plus 1. That's the only time we need it. There may be other non-zero entries in this row, but they won't be affected because this term would be 0 after K equals J plus 1. So this innermost loop also gone. And now wherever I see K, I can replace it with J plus 1. So yeah, I'm going to move things up a bit. and fix my indentation. And then I'll just rewrite this line up here with k equal to j plus 1. That's it. Not much of an algorithm left. Okay, so only 2 lines needed per column. To carry out the row operation. Questions about how that was arrived at? Those are the substitutions that were made. Now, one thing that we have to deal with abandoned matrices in general, not just tridiagonal, is storage. Normally, a vector is represented as a 2-dimensional array, but when you have a banded matrix of low bandwidth, most of the entries would be 0. We don't want to store all those 0 entries. We use a vector for each diagonal, each non-zero diagonal. So from a tridiagonal case, I'll use A for the main diagonal. Actually, you need to check my notation. Yes. Okay. And then I'll use L for the subdiagonal. And then U for the superdiagonal. L will be the superdiagonal of A at first, and then the subdiagonal of L after modifying it. Same thing here. U will at first be the superdiagonal of A, and then after this is finished, it'll be the superdiagonal of U. So we're going to overwrite. So now what I'll do is modify this algorithm. Going to carry out the same steps, but the notation will change to use these vectors. All right, so if it should be a 1. Okay, so j plus 1j, that is a subdiagonal entry. So I'll just use L, and I'm going to use the column index for L because the column index for subdiagonal entries will start at 1. So Lj is equal to itself divided by the j's diagonal entry, which is now called Aj. Everything's going to have a single index now. So this is the original subdiagonal entry. This is a multiplier. Then from a main step, a row operation, on the left side, we have a diagonal entry. Well, row and column index are the same, so we just take that single index. So the Aj plus 1 is what gets changed, and it's equal to itself minus the multiplier from the step above. And then j plus 1, that is a super diagonal entry. We identify those by the row index because that starts at 1. So we have LJ, UJ. And that's it. So this is the vector storage version of Gaussian elimination for a tri-diagonal matrix. For a more general banded matrix, there would be some more work involved. For instance, if it's a pentadiagonal matrix, you could eliminate 2 entries per column, and you'd have 2 operations like this, carry up to row operation. In the notes, I have stripped down versions of forward and back substitution, same idea, where you move any unnecessary loops and then use this vector storage. Questions about how this was heavily condensed? Now, one problem when it comes to banded matrices. No, I haven't said anything so far about pivoting. So all of this is Gaussian elimination without pivoting. But if you do use pivoting, it absolutely destroys bandedness. And you get a phenomenon which is called fill-in. And what fill-in means is you get non-zeros entries outside the band. So you lose the advantage in efficiency that you gain from Gaussian elimination on a banded matrix, because you're causing the matrix's bandwidth to increase. In worst case, could become not even a banded matrix anymore. It could be like a full matrix. Well, I wouldn't say you can't use pivoting, because sometimes you really need to. Like what if you have to divide by 0? You have no choice. Now, what you can do is as a compromise is use a more relaxed pivoting scheme. What I mean by that is, like in partial pivoting or complete pivoting, you're requiring that your multipliers be no larger than 1 in magnitude. So what if you don't require that the multipliers be less than or equal to 1, maybe less than or equal to some number value L. So you're still trying to limit the propagation of round-off error from Gaussian elimination by at least limiting the multiplier size. You don't want them to get arbitrarily large. But not, so maybe, so if you're going to interchange rows, because you're in danger of having a large multiplier, and maybe you settle for a second best, like whatever's going to do the least damage to sparsity. So it's not great, but all we can do. So, and this is why for sparse matrices, often iterative methods are used instead. Well, there are a lot of reasons to use iterative methods, and sparsity is one of them. Because then you're not doing something that's going to destroy the sparsity or bandedness in this case. All right. one of my standard oral final questions. We don't have that in this class, but, I guess in 561 we did.
L greater than R.
L greater than 1. Yeah. Yeah, since L is 1 in the case of ordinary pivoting schemes. Okay,
Just share, I can read later.
actually, it's a different letter. It's L is the LE factorization. Okay, you mean an example of fill-in? Okay,
If it's relevant, of course.
um,
I mean, sorry, example of relaxed filter.
oh,
If it's relevant, otherwise.
not really, no. Yeah, like, okay, what I could, like, to implement something like that, when you require multiplier to less or equal to 1, there's only, chances are, unless there's a tie, there's really only one row you can swap with. But if you raise this threshold, you may have multiple rows where such a swap is possible. And you might choose, like, for instance, if you're working in column J and you have various I values, row indices that are greater than J that you could swap with and satisfy this condition, I would probably choose the I that is closest to J, because then, yeah, it affects things tremendous less.
If you switch the row directly below, you only have one.
Yeah, one, yeah, exactly. Yeah. Whereas you're gonna swap like the first and the last row, and you're just asking for trouble. Yeah.
It should just, yeah.
Yeah, it's just like, oh, you don't want a banded matrix, okay, yeah. Okay. All right, so that's all I have to say about banded matrices, and still have a good amount of time to deal with the other category of special matrices, that is metric positive definite. There's a whole section of notes about just plain old symmetric. I'm skipping it because there are no homework problems on it. Actually, there are not many homework problems in this section at all. And no MATLAB problem. Okay. Okay. So matrix A is metric positive definite. If first have to be symmetric. A equals A transpose. By the way, I'm going to assume throughout this discussion, and actually most of, pretty much the whole semester, that we're dealing for real matrix. If A is allowed to be complex, I would not want the transpose, I would want the Hermitian transpose, which is written as AH, and that's transpose and complex conjugate. So when you're generalizing something from real matrices to complex, if you have a transpose, chances are it should be replaced by the Hermitian transpose, and then whatever you're doing can generalize. So that's all I'm going to say about complex. So first it has to be symmetric. And what makes it positive definite on top of being symmetric is this quantity, X transpose AX, which is just a number, has to be strictly positive for any non-zero vector X. So apparently it depends on who you ask, but like if you have a matrix that satisfies just this condition and it's not symmetric, blue chalk dust all over my hands. If it's not symmetric but satisfies this condition, some books say that it's still not called positive definite, and some books say it is, so I don't know. So, to be on the safe side, if C matrix described as just using just the words positive definite, there may be an implied symmetry to it also. So like sometimes mathematicians don't agree on what should be called what, because we need more complexity in mathematics. Okay, now you could think of a also the common abbreviation referred to it as SPD. For laziness. So you could
Name of the Power Ranger show.
SPD.
Yeah, Space Patrol Delta.
Oh, okay, good enough. Wow. Okay. You know if the Power Rangers actually get charged with murder or something, or?
Yes.
Okay.
It was.
Yeah.
It was.
Yeah, but that was a totally, yeah, because Power Rangers not even on my radar until I heard that. It's like, yeah, okay. Anyhow, so you can think of a symmetric positive definite matrix as the generalization to n by n matrices of the notion of a positive number. Okay, so I guess you think of a positive real number as a 1 by 1 SPD matrix. Okay, so here's some properties that SPD matrices have. First, A is invertible, also known as non-singular. The determinant is positive. Okay. All of the diagonal entries must be positive. You can have negative entries in an SPD matrix, but it just can't be in a diagonal. So this would be one way to it's not always easy to tell just by looking if a matrix is SPD, but you can rule out being SPD if you see like a negative diagonal entry. Okay. The largest entry has to be on a diagonal. There's a kind of sort of diagonal dominance. It's not strict diagonal dominance, but to an SPD matrix. And this property could also be taken to be like an equivalent definition of SPD. All the eigenvalues are strictly positive. In fact, this property implies this one because the determinant is a product of all the eigenvalues. This one you can very quickly prove must be true because we just set X equal to EI, the ith column of identity, then X transpose AX is AII. That has to be positive. Okay. This one you can show by setting X equal to an eigenvector. Then X transpose AX would be X transpose X times the eigenvalue.
Do we have to do the checking if it's not given?
Sorry, what?
Do we have to perform all the checks?
Oh, like to find out if matrix is SPD? No. Well,
If we don't know.
I'll come to that when we talk about solving systems. Okay, now. Well, okay, So another property is that all of the right. So A is SPD if and only if. Actually, this is also an if and only if. Assuming A is symmetric in the first place. So a symmetric matrix has real eigenvalues. If those real eigenvalues are also positive. So if it's already given to be symmetric, it's also PD if and only if the eigenvalues are positive. Okay. A is also SPD if and only if. And I'm trying to remember the notation I use for this. Hold on. Okay, these are the principal minors. I mentioned these last time about the LU decomposition. LU exists if and only if all the principal minors are non-zero. Is this notation I use for them?
Yeah.
Okay, good. Nice to know I'm thinking the same way from one day to the next, because me, you never know. So they had to deposit. So in fact, this property implies this one because the determinant is the n principal minor. So because all of the principal minors are positive, therefore, of course, non-zero. LU exists. So every symmetric positive definite matrix has an LU decomposition. Okay. Now, so what that means is, if you want to carry out Gaussian elimination on symmetric positive definite matrix, you'll know that it is never absolutely necessary to pivot. You're no danger of having like a zero diagonal entry to go in your multiplier. I actually have a comment here in my notes, and I have to look up like where did I find this? Because it also says Gaussian elimination for the SPD matrix is robust with respect to accumulation of round-off error. Because recall there are two reasons to pivot. One is if you end up having a zero diagonal entry, so you must pivot, but also pivot to get smaller multipliers to prevent accumulation of round-off error. And so it's natural to think for an SPD matrix, well, okay, you never are in danger of having zero diagonal entry, but you could, what if you are in danger of having a small multiplier that could still propagate a large multiplier, could propagate round-off error. But apparently that's not necessarily the case. And unfortunately, I don't recall why that is. And so my notes are not complete in that respect. But it actually makes sense to me because of this. You get the largest entries in the diagonal. So that could have the effect of limiting the size of the multipliers. Okay. So then I'm thinking, okay, if I have AX equals B, and I know that A is SPD, I can just do Gaussian elimination of pivoting and I'm good. No. It's fine, but it's not the best idea. And the reason why is because it's not the most efficient way to go. There's an alternative. Yeah. Yeah.
Are we talking about each row and each column wise?
Not necessarily.
Okay.
I'm just saying the one largest entry in the entire matrix has to be somewhere in the diagonal. Yeah, you may have smaller entries on it, but
What I was thinking, but that was the reason for pivoting.
yeah. But for example, like it's supposed to look at, say the second, principal minor. So that'd be the determinant, like so you're talking about A11, A12, A21, which equals A12, A22. All right, so the second principal, first principal minor is A11. Second principal minor is determined this matrix, and it has to be positive. So we get the following: A11, A22 minus A12 squared has to be positive. One of these has to be a lot bigger than this, for that to be true. So that sort of thing helps limit multiplier size. Okay, I should check on that though, because I don't even remember where I read that comment. All right, so how do you solve Ax equals B? The process is quite similar to what you do for a general matrix with Gauss elimination. What you do is called the Cholesky. What? And apparently that's a traumatic memory.
Just challenging.
Okay. Actually, my advisor, Gene Gall, his computer at his office was Cholesky.stanford.edu. So A is equal to G times G transpose. And G is lower triangular and has positive diagonal entries. So what?
This is a differential.
Okay.
The big matrix.
Yeah. Yeah. I'm not sure if I feel like doing it today, but all right. So so since the left factor is lower triangular and this is upper triangular, it's very much like Euclidean decomposition. It's still that type of factorization. It's just that now the factors, instead of having a unit lower triangular and some upper triangular, you have a triangular factors being each other's transpose, which makes sense that you're going to get that because of the symmetry. Okay. Very often when you need to prove something about symmetric positive definite matrices, it's a good idea to take into account that it has a Cholesky factorization. So yeah, actually, so a matrix has a Cholesky factorization if and only if it is SPD. And so there's a hint I would often give for proving something involving an SPD matrix, like I'll use Cholesky factorization. And I guess I was so insistent with that hint in various classes, like this one or 561, that the annual evaluations one year, the student was actually my co-author, Amber Sumner. She wrote for her evaluation comment, when I think SPD, I think Cholesky. And so it's like, okay, it's good that it's sunk in. Now, here's the irony. I have assigned on the homework one problem from this portion of section 3.3 that deals with SPD matrices. And for that particular problem, you do not need Cholesky. But most of the time, you do. So I was realizing, like, oh, not that problem. Like, yeah, don't want to send you down the wrong track. So usually you use Cholesky. Okay. And then once you do, just like you do for the general case, you do forward substitution of Ly equals B and back substitution of Ux equals Y. It's similar. You take the lower triangular factors, so G, Y equal to B. And then you solve G transpose X is equal to Y. So here you use forward substitution, and here you use back substitution. This process requires 1/3 n cubed floating point operations. That's why we use Cholesky instead of Gauss elimination. Even though Gauss elimination would work well, it's going to be twice as costly. But Cholesky factorization exploits the symmetry of A to get the job done in half the time. Okay. All right, so I'm going to write out the Cholesky algorithm. That's very similar to Gauss elimination for effects. So for one thing, you loop over all the columns. So you're going to generate the Cholesky factor G one column at a time. Okay. You start by taking a square root of whatever diagonal entry you're on. So this is in this respect very different from Gauss elimination, which doesn't involve any square roots. And then you loop over rows below a diagonal, just like in Gauss elimination. I need to give myself more room. And here you're setting an element of your lower triangular factor, just like you're setting a multiplier in Gauss elimination. And in fact, the formula is largely the same, Aij, but over Gjj in this case, instead of Ajj. And then you perform something that's kind of like a row operation in a way. Like the structure of a loop is exactly the same. And you'll have Aik is equal to itself minus this kind of sort of multiplier. G, but there you have an entry of G, Kj. Okay. So it's not exactly a row operation. So this entry that we're taking the square root of, it's not the first time around, it's the original A11, but every iteration after that, it's an updated diagonal entry that we're taking the square root of. Okay. I should mention what's happening here. If A is equal to GG transpose, that's the same as a sum of what are called outer products. So vector GJ, a column vector, times its own transpose. When you take a column vector times a row vector in that order, the result is a matrix. This is called an outer product. The transpose is on the outside. If it's transpose on the inside, like A transpose B, that is an inner product, also known as a dot product. Where G, the matrix G, has these vectors, G1, G2, and so forth, as columns. Okay. So what this algorithm does is when J is equal to 1, it computes G1, the vector G1, to the entire first column of capital G. And then this right here is updating A by subtracting off the J outer product. So we compute G1, we subtract off G1 transpose from A, and then we're working on the rest of A. So second time through, it'll compute G2, subtract off G2 transpose, keep going until nothing is left. So from a matrix multiplication point of view, this is what this algorithm is doing. So the idea is this here, these two lines are meant to compute the vector Gj before subtracting off the outer product. In fact, the outer product of two vectors is a matrix consisting of all possible pairwise products of elements of both vectors. So this right here is a single element of this outer product. That's actually the, yeah, so this right here is the IK entry of Gj transpose.
Gj to be a column vector.
Sorry, what?
We're assuming Gj as a column vector.
Yes. Yeah, all vectors are column vectors. If you want a row vector, take a transpose. Okay. All right. Okay. Now I'm going to carry out this algorithm on a very simple case. A matrix that's actually, what? Yes,
When we're computing Gj.
Yeah.
We are going to get like separate column vectors for Gj. Right?
well, so Gj is one column vector.
Exactly, so for that first column.
Yeah, and we fill in all the entries of it during the J iteration.
Okay, and in the last part, it's going to change that A to
Yeah.
two entry.
Yes,
And then it's going to continue.
yes. Yeah, so basically, we're whittling A down. Because to compute G2, we need to get G1 out of the way. Yeah. There's also the first row and first column of A come only from G1. So once we compute G1 and we subtract off G1 transpose, the modified A will have nothing in the first row and column. So it's like we've whittled the matrix down to like n-1 by n-1. Yes. Yeah, James is making the right gestures here. And yeah, it's like that. And yeah. And then, so it's like you're starting anew on, so it's like G2 comes from the first part of the trimmed down A. And this just keeps going until A is gone.
Replace basically.
Yeah.
And by that logic, each vector that we get will be the same size because it is a bounded matrix, so.
These are all the same size except, but one thing about them is like in G1 is generally a full vector, whereas G2, the first entry in G2 will be 0.
Yeah.
And yeah, it's from a triangularity.
That's what I.
Yeah.
But otherwise they wouldn't be.
Yeah.
the same.
Yes. Yes, each one is a vector of like that.
I got a bit lost because of our product.
Oh, okay. Very quick example of an outer product. If I let U equal AB, B equal CD, then UV transpose is B times DB. And if you carry out the regular matrix multiplication process, it turns out to be AC, AD, BC, BDs. So every row of an outer product is a scalar multiple of a row vector. Every column of dotted product is a scalar multiple of a column vector. What that means is, as long as both vectors are non-zero, a dotted product always has rank 1. And in fact, every rank 1 matrix can be described as not a product. Okay. But yeah, this matrix here is actually not symmetric, positive, definite. But the determinant is negative. Yeah. But I want to show you what happens when I try this algorithm on anyway. So let's see what happens. We have G11 is equal to the square root of 1 entry, so that's 2, that's fine. And then we do G21 is going to be 4 over 2, so that's going to be 2. Okay, and then, oh wait, no, that's wrong. G21 is equal to A21, which is 3. So it turns out to be 3/2. Okay, whoops. Sorry about that. And now, when I go to modify A, so A, okay, so I is equal to 2 and K is also equal to 2. So A22 is equal to itself minus G21, G21. So we have squared. So it's going to be equal to 2 minus 9/4. So it's equal to minus 1/4. So all of this is for J is equal to 1. Now, when J is equal to 2, we have G22 is going to be the square root of minus 1/4. And the algorithm breaks down. So it turns out that the Cholesky factorization algorithm is really also a good way to check if a symmetric matrix is also positive definite, because if it's not, the algorithm is going to break down sometime. So either you're taking the square root of a negative number, or if this is 0, you're going to be dividing by 0 later. So something's going to go wrong. Really, this is no less efficient than if you were going to try to compute all the principal minors and check that they're positive. Actually, this might be even more efficient. So this is how you check. Just try Cholesky and see if it crashes. But one problem in the section I didn't assign it is, okay, you go ahead and write a MATLAB function to implement Cholesky factorization, but also have it return a second output indicating whether the matrix is positive definite, because it's going to find out. Okay. Are there any questions about the Cholesky algorithm? All right, the last thing I'll say is actually about symmetric matrices, but it also applies to SPD. And this is written up in much greater detail in the notes, but I just don't want to neglect it entirely. A is symmetric. Whether positive or definite or not. Use this factorization. A is equal to LD L transpose, so the L referred to as the LDLT factorization, where L is unit lower triangular, just like the L from Gauss elimination. In fact, it literally is the L from Gauss elimination. And B is a diagonal matrix that ought to have all non-zero diagonal entries. So you can think of D times L transpose, that's like the U. Okay. So, and this takes also 1/3 NQ flops. It's It points to symmetry for efficiency. So again, a better big Gauss illumination for a symmetric matrix. And if your matrix is symmetric, positive, definite, you can certainly use this for it too. So that's why LDLT is known informally as square root 3 Cholesky. Because it does not, the algorithm for it, which is in the notes, does not involve taking any square roots. In fact, there's a close relationship between LDLT factorization and Cholesky. G is equal to L times D to the 1/2. Now, if your matrix is symmetric, but it is not PD, the LDLT factorization might not necessarily exist, just like LU doesn't always exist. It may be necessary to pivot. So one thing you want to be careful about is if you are using pivoting, what we must do is swap rows and columns. And the reason for that's the only way to preserve the symmetry of your matrix. So then what you have there is PAP transpose is equal to LDL transpose. So you have a row and column swapped version of A, and then the LDLT factorization would exist for that. And then you have to take that P and P transpose into account in whatever triangular systems you're going to solve using LD and L transpose. Okay. Last thing I'll say, there are MATLAB functions for these. There's Chol for Cholesky factorization, but that uses a different convention for Cholesky factorization than what I showed here. A is equal to R transpose R. R is upper triangle. So, in other words, R is equal to G transpose. So it's still lower times upper. It's just identified differently. And then there's also LDL function to compute the LDLT factorization. Okay, just like there's a LU function for LU, which I forgot to mention last time. Okay. Well, I'm over time anyway, so got through it all, but well, because I skipped the LDL part. But yeah. Yeah, I'm gonna be so pissed at myself if I look at the next set of notes and find I have like a billion pages again. I write too much. Can't shut up. Okay.